Okay, let's continue our class. Now I'm going to speak about some special cases where our functional problem has some constraints. We spoke about constraints. We know that our functional problem may have two different kind of constraints. We may have integral constraints or function constraints. First of all, I'm going to speak about integral constraints, and then we will speak about function constraints. Let's say that our problem is to find the function y, which is going to have which is going to give an extremum amount for the functional I, but at the same time y cannot be any function. There is some restriction on the function y of x, and y of x must satisfy this integration, which is known as J is integration from x1 to x2 of g of x and y dash d x. It must be a constant given number. This is our new problem. We want to find the extremum value of y tilde, but at the same time of y, but at the same time y must satisfy the following boundary conditions, equation 233. Okay, at this kind of problems, we now define again y tilde of x as a set of varied paths from y of x, where y of x is our solution. But in the definition of y tilde of x, we have some new definition for y tilde of x. Let's say that at this new definition we define I tilde as we defined before, is integration from x1 to x2 of f of x, y tilde and y tilde dash dx, and j tilde is integration from x1 to x2 of g of x, y tilde and y tilde dash dx, where y tilde the varied path, the set of varied passes from y of x still satisfy our constraint. This is very important because it's very important because if y tilde does not satisfy this boundary condition, it is not easy to find y of x by this equation. Let me continue. Let's go to our next slide. Okay, to do so, I'm going to define y tilde x as follows, where y tilde of x is y of x plus epsilon 1 eta 1 of x plus epsilon 2 eta 2 of x. Okay, now we can say that eta 1 and eta 2 are any arbitrary function if I know the value of y at x1 and x2, or we know that y of x1 is y1 and y of x2 is y2, we can say that eta 1 and eta 2 vanish at the endpoints x1 and x2, or in another word, eta 1 of x1 is 0, eta 1 of x2 is 0, eta 2 of x1 is 0, eta 2 of x2 is 0. And now we can say that I tilde is function of two variables, epsilon 1 and epsilon 2. I tilde is a function of epsilon 1 and epsilon 2 and can be defined as integration from x1 to x2 of f of x y tilde and y tilde dash dx, and j tilde in the same way is function of two parameters, epsilon 1 and epsilon 2, and can be defined as integration from x1 to x2 of g of x y tilde and y tilde dash dx. We know that if epsilon 1 and epsilon 2 tends to 0, or in other words, if y tilde tends to y, I tilde and j tilde I tilde has its external value, or in another word, we can say that the first variation of I tilde, which can be defined as follows: partial derivative of I tilde with respect to epsilon 1 at epsilon 1 and epsilon 2 is 0, multiplied by epsilon 1 plus first variation of I tilde with respect to epsilon 2 at epsilon 1 and epsilon 2 is 0, multiplied by epsilon 2 must be 0. And in the same way, when we told that we choose the set of y tilde in the way that this integration has a constant number. If we have a constant number, we can easily say that the variation of a constant number is 0. So we can easily say that the first variation of j tilde is equals to 0, 2, which leads to the to this equation 238. And there is some important point I must mention. You must know that epsilon 1 and epsilon 2 are not independent of each other, because if we know the value of epsilon 1, we can say that the value of epsilon 2 must be determined in the way that this integration has our constant number. So we define, we sum these two equations. We multiplied the second equation. We multiplied the second equation, equation 238 by delta, and calculate the summation of equation 231 plus 238, as you can see here, by equation 239. In this equation, we define lambda as the Lagrange multiplier. We know that epsilon 1 is an independent variable, but epsilon 2 is not an independent variable, and epsilon 2, the value of epsilon 2 is changing by the value of epsilon 1. Okay, we know that epsilon 1 has the arbitrary amount, has an uh, is a variable which is not a zero, which is not zero. So we can easily say that, let's look at here, the coefficient of epsilon 1 must be 0 in order to have the zero value for all values of epsilon 1. And we know that epsilon 2 is a function of epsilon 1 and is changing by the value of epsilon 1. So we can say that the value of epsilon 2 is not necessarily 0, so we can conclude that the coefficient of epsilon 2 must be 0 too. Setting this coefficient equals to 0 leads to two equations 240 and 241, which are the same equations as if we do I'm sorry, if we do differentiation, we can easily say that these equations leads to the same equations. Now we can easily define the new function I tilde star, which is equals to I tilde plus lambda multiplied by j tilde, where lambda is an unknown parameter which is known as Lagrange multiplier, and we can easily say that partial derivative of I tilde star with respect to epsilon 1 is equals to 0, and partial derivative of I tilde star with respect to epsilon 2 is equals to 0 at epsilon 1 is 0 and epsilon 2 is 0. If I replace I tilde star in this equation, we reach to the following functional problem. In this functional problem, f star is defined as f plus lambda multiplied by g, and if we do derivation and using integration by parts, we can easily show that we can easily reach to this equation. This is very important. Partial derivative of f star with respect to y minus d over dx of partial derivative of f star with respect to y dash multiplied by eta I d of x is equals to 0, because eta i's are any arbitrary function with admissible boundary conditions. We can easily say that the coefficient of eta I must be 0, which leads to this equation. This is our last equation, which is known as Euler-Lagrange equation with integral boundary condition. In this equation, our unknowns are y and lambda. In order to find these two unknowns, y of x and lambda is a parameter, we can easily use our boundary conditions. So this equation, along with our boundary condition, is our main equations to find the value of y of x. If we have, in the same way, if we have n constraints or n integral constraints, let's say integration from x1 to x2 of gk of x, y and y dash dx is equals to ck, we defined f star as follows. We can see here f star is f plus summation of k from 1 to n of lambda k multiplied by gk. Substituting this equation into Euler-Lagrange equations leads to an ordinary differential equations with n plus 1 unknowns, let's say y and lambda 1 and lambda 2 till lambda n are n unknowns. To find these n unknowns, we use this equation, Euler-Lagrange equations, along with our constraints. We can find our n plus 1 unknowns. This is how we can use a variational method to solve functional problem with integral constraint. Let's now speak about an example to make this subject more clear. Let's recall our first problem we introduced at our first lectures. I'm going to speak about isoperimetric problem. In isoperimetric problem, as you may know, we are going to find the shape of the closed loop path with lengths of L, which have the greatest area. We have shown that at that problem, I or the value of area can be calculated by this formulation, and integral from t1 to t2 of x dy over d tau minus y dx over d tau multiplied by d tau, where tau is a parameter, is where x and y is the parameter of tau, and L, the length of the path, can be calculated by this formula, integration from tau 1 to tau 2, square roots of dx over d tau by 2 plus dy over d tau by 2 d tau. This is our functional problem, and this is our constraint. Using previous definitions, we can easily say that f star is equals to f plus lambda g, and we can say that f star is 1/2 of x y dot minus y x dot plus lambda x dot by 2 plus y dot by 2, all of them power to 1 over 2. This is our new function f star, and we can rewrite equations of Euler-Lagrange equations for this set of problems to find the value of x1 and the value of x and y. First of all, let's say that in this problem we have two unknowns, so we must write Euler-Lagrange equations for two variables. We can say that partial derivative of f star with respect to x minus d over d tau of partial derivative of f star with respect to x dot is 0. This leads, if we do derivation, it's very easy. If we do derivation, we can easily reach to equation C, and we can do the same for y. We can say that partial derivative of f star with respect to y minus d over d tau of partial derivative of f star with respect to y dot is equals to 0, and we can reach to these differential equations. Now we can easily integrate these equations with respect to tau. If we do so, we can say that y over 2 minus the equation in the brackets is equals to a constant number. If I sum y over 2 plus y over 2, I have y, and I can do the same for the second equation, equation D, and I reached to these equations, and in these equations I can eliminate. Let's look at here. I can easily eliminate lambda from these equations if I if I use lambda from equation 1, and if I equation E, and if I calculate lambda from equation F, and set these two equations equals to each other, set these two lambdas equals to each other, we can reach the following result: x minus c2 dx plus y minus c1 dy is 0. Okay, and we can easily integrate this equation. This equation is very easy to integrate. Integration of this equation with respect to x is equals to x minus c2 by 2 over 2 plus y minus c1 by 2 over 2 is equals to, let's say, a parameter c3 by 2. Okay, this is our last equation. In this equation, we have three unknowns: C1, C2, and C3. We know that the boundary conditions, or boundary conditions, give the value of C1 and C2. And from this equation H, we can easily say that equation H is showing the equation of a circle at the center of C1, C2, and C1 with the radius of square roots of 2 multiplied by C3. And I mentioned it here, and this equation, or this parameter, is helping us to find, we can calculate the value of C3, because we know the total length of the rope, or we know that the total length of the rope, or 2pr is equals to L. We know LR is equals to this parameter, and we can easily calculate C3, which is relevant to our unknown lambda. So the value of Lagrange multiplier lambda is calculated solving these equations. Okay, it's enough for now. I hope to see you soon. In our next session, we are going to speak about constraints, different kind of constraints or function constraints, and we are going to speak how to solve the functional problem when we have function constraint. It's enough for now. Hope to see you soon, and bye.